Thank you very much. So, of course, I would like to thank Rafael and Tony and Mati for accepting the talk. And so this is a collaboration, actually, with Rafael and with Daniel. And it's about multipartite Bell non-locality and classical causal networks. So the first thing, so I guess that so as a motivation of the talk, I guess that I mean, I can say that almost probably everybody here knows that in the bipartite scenario, local hidden variable models can be described that they have associated such a causal structure, right? So I'm going to be talking about correlations. So we have the scenario of black boxes. So in this case, X and Y are inputs of Alice and Bob's measurements that get outcomes A and B. And local hidden variable models can be represented graphically by this causal structure, right? And of course, as we know, Bell's theorem says that quantum states can produce correlations that are incompatible with these causal structures, right? So lambda here is the hidden variable, right? And so there are two assumptions in Bell's theorem, of course, and so so what we call causal assumptions, right? So the first one is the assumption of locality, namely that, for instance, there is no causal influence from X to B, so from Alice's input to Bob's output, and this is what we call locality. It's an assumption. And then the assumption of measurement independence, right? The fact that both Alice and Bob can choose their measurements freely, uncorrelated from the underlying hidden variable in the hidden variable model, right? And these things have been studied. These relaxations, these causal relaxations, have been studied, of course, in the bipartite scenario. And what is known is that a single causal in this scenario, any single causal relaxation, so namely any arrow that I draw, so any extra arrow that I put starting from this causal structure leads me to correlations that fill all non-local correlations, right? So so there is let's say so it's interesting to characterize causal relaxations because they shed light on the nature of non-local correlations, and also they give natural ways of quantifying them, right? So in the bipartite scenario, it's not, in a sense, not so funny because any single causal relaxation enables you to reproduce all non-local correlations, but this is not the case in the multipartite scenario, right? So the first works in these directions, are due to Svetlichny almost 30 years ago, right? So this gave rise actually to the notion of genuinely multipartite Bell non-locality, right? So these were the Svetlichny's B local hidden variable models, where somehow there is a natural split in the system here. And here we see, for instance, that Bob's output is influenced by Alice's inputs, and also Alice's output by Bob's input. But the funny thing about, one of the interesting things about these models is that they satisfy something that is called the Svetlichny inequality, that probably most of you have heard of, and which is violated by quantum correlations, right? And also this thing, so this is the input broadcasting model. It's a different. So again, two causal relaxations, and also this model satisfies Svetlichny inequality, right? So so there is a nice paper. Let's say that more or less treats this in a general way, where they look at this. So now I'm looking, let's say, at the same situation as before, but from above. So here I have 4 users. I'm not plotting the hidden variable and the input and the output of each user. I'm looking at the user from above, and each arrow here represents a dependence of. So for instance, this arrow here represents that the output of this party depends on the input of this one. So essentially, each arrow is a communication sending the input from one party to another, right? And so in this paper, they define something that's called partially paired correlations. So these are the correlations such that there is a pair, such that no output depends on both inputs of the pair. So for instance here, so you see that these two, so this pair, there is no party, there is none of these 4 circles that receives the input of both these circles, right? So they characterize them. They said they called, so these people, this author characterized the correlations that you produce by such communication patterns, and they call them partially paired correlations. And they prove that they also satisfy Schmidt-Lichny inequality. So it's kind of a nice it was kind of a nice result, because you see that there's lots of communication allowed here, but still these satisfy Schmidt-Lichny inequality. And since Schmidt-Lichny inequality is violated by quantum correlations, so one of the claims in that paper was that quantum correlations are more non-local, even more non-local than generally multipartite non-locality in the sense of Schmidt-Lichny. No? So this pattern here, it definitely looks as it allows more correlations than the Schmidt-Lichny graph, right? And there was an open question there. So they define so let's say these are the partially paired correlations, and then they define the totally paired correlations, which is so everything that is not in that does not correspond to this graph. So for every pair, there is an output that depends on both inputs of the pair. So there is a party. So for every pair of parties, there is one party that receives the inputs of both members of the pair, right? So for instance here, right? So if I look at these two parties, then this one receives both inputs. So the output of this one depends on its own input and on the input of this one. Then, so for these two, the same situation. The output of this one depends on its own input and on the input of this one. And for these two, the output of this one depends on its own input and the input of this one, right? Right. So one thing that they found is that these do not satisfy Schmidt-Lichny inequality, which is kind of, at first sight, one would say that this is kind of surprising, because this one looks, so this looks like there are more locality relaxations here than this one, but these people prove that this type of correlations associated to these structures do not satisfy Schmidt-Lichny inequality, and they left us an open question whether there would be quantum correlations incompatible with these communication structures, right? So quantum correlations more non-local than totally paired correlations. So this is one of the questions that we will answer here, but this will be actually an application of the method that we have for studying, let's say, for studying generic causal relaxations, right? So what we see is that causal relaxations give like a natural way of defining, in a sense, classes of Bell correlations, right? And what we address in this work is methods to, let's say, a unifying, a systematic characterization of all the multipartite causal relaxation, right? So this is what we will do, and there will be essentially so this is the outline. I will be talking of the no signaling principle as a method, let's say, as a tool to establish equivalences between different causal structures, and this will lead us to the characterization of the classes, which will end with something that we call causal hierarchy, and then something that I like to call multipartite super non-locality, in the sense of being quantum correlations stronger than totally paired correlations, in the sense that I said in the previous slide. And then I will devote one slide to non-trivial Venn inequalities without a quantum advantage. So I guess this type of slides has been shown already in the last couple of days. So these are classical causal models that are given by the framework of Bayesian networks. And Bayesian networks rely on these directed acyclic graphs, right? That encode, let's say, a causal influence between different events, right? So this is something that can have many applications in different fields of science, right? So here we see a model of rush hour, and this influence traffic jams, which is also influenced by bad weather and accident and so on. And the formal definition, so you say that, let's say, classical causal model specifies a DAG, right? And each node of the DAG encodes a random variable. And the classical causal model has also probability distribution P, which is Markov with respect to this DAG, right? And the Markov condition namely says, so this is also the terminology, the genealogical terminology that has been mentioned also. So this PA of variable VI refers to the set of parents of variable I, right? So So for instance, here the sirens is the child of accident, and accident is the parent of the siren, right? And there is an equivalent formulation in terms of conditional independence conditions that has been also mentioned. So with this framework, so we want to look at DAGs relevant for Bell scenarios, right? So not all, we're not interested in all DAGs here. We're interested in the DAGs that appear in Bell scenarios, which have two common properties, right? So namely, so all of them have an unobserved hidden variable, lambda here, and they all have two sets of observable ones, the inputs and the outputs, right? So very natural, the DAGs that we use for Bell experiments, right? With a condition also that the hidden variable is a parent of all the outputs, right? So there is always an arrow from lambda to the outputs. There is always an arrow from each input to its own output, and then we will play here with extra arrows, starting from this situation, right? So right, but of course these things are very complex. No, I mean, if you, let's say, as you increase the number of parts, these BDAGs, even with those properties, it's still highly complex objects, and the question is how to classify them in a practical way. And of course, we use the no signaling principle that imposes extra constraints, right? So we use something that we call that we like to call no signaling equivalence. It's a very natural definition. So assume that you have two DAGs, G1 and G2, and then we say that the DAG G1 is no signaling implied by G2 if all no signaling correlations produced by distributions Markov with respect to G2 are also produced by correlations Markov with respect to G1, right? And then we say that G1 and G2 are no signaling equivalent if they imply each other, right? So here, I don't know, I have a kind of a rustic representation of the signaling simplex and the no signaling polytope, and this is very hand-waving. These two objects live even in spaces with different dimensionality, right? So this is just a very schematic picture. So we look at two DAGs, G1 and G2, and each of them has an associated causal polytope, right? And these things can differ. I mean, for different G1 and G2, you can have different causal polytopes, but then what we do is to look at the intersection between the causal polytope and the no signaling polytope, right? So very natural thing to look at, and we say that. So we say that G1 and G2 are no signaling equivalent if, well, the intersection between the causal polytopes of each DAG and the no signaling polytope is the same, right? So this is what we call no signaling equivalence, and then we have two technical lemmas, right? So all the causal hierarchy that we build rely on two technical lemmas. So one of them is simply, let's say that you can sort of, when you're trying, so for instance here, right? So you look at a bipartite BDAG, and then there are many ways in which you can relax locality, right? So for instance, if you count the number of ways of drawing arrows from Alice to Bob, you see that there are 15 different ways of drawing arrows, right? And then what we prove is that the most general one in which you draw all the arrows from Alice to Bob's side is actually no signaling equivalent to this one, where you have a single arrow from the input of Alice to the output of Bob, right? It's kind of an intuitive thing, but we prove it formally using the framework of Bayesian networks, right? And in the case, for instance, where you have a subset of the arrows here, then it's included, right? So I mean, this is the most general situation, the most general locality relaxation. This is equivalent to this one in the no signaling framework, and whatever situation with less arrows here is contained in that too. So in a sense, this kind of include all the, let's say this one is the most general way. Let's say these include all the correlations that can be attained also by these relaxations in the no signaling framework. And then the other technical lemma that we have is about measurement independence. So remember, so the first slide that I showed was about the assumptions in Bell's theorem, right? So there were two fundamental assumptions, locality and measurement independence. So we look at this so we relax this assumption here, and we deal with that with this lemma. So now we look at situations where you draw an arrow from lambda to x1 or from x1 to lambda, and then what we prove is that in the end of the day, this is no signaling equivalent to this situation in which having an arrow connecting lambda and x1, then you have a broadcasting of the input x1 to all the outputs, right? So in a sense, so we see that in the end of the day, what matters is non-locality relaxations from inputs to outputs, right? In both situations, we arrive at the conclusion that in the end of the day, all we have to look at is locality relaxations from input to outputs, right? So, so let's say they are, so each input to output BDAG, so each input to output locality relaxation captures all possible causal relaxations and gives like a more practical way to organize the different causal models, right? So that's why we take input-output BDAGs as representatives of causal classes. So we define, so let's say we define causal classes that are represented by an input-output BDAG. And we call them, causal Bell classes, which is simply the convex hull of all no signaling correlations compatible with a given IO BDAG or its party exchanges, right? Of course, we don't, let's say, so permutations of the same BDAG doesn't lead us to a different class, right? We take convex combinations of all the correlations compatible with all the permutations of a given IO BDAG. And what I present here is the complete causal hierarchy for tripartite systems, right? So so here you see, so this is the original LHV model. There is no causal relaxation here. Then the first level, so this is like the 0 level. The first level, you allow for one causal relaxation, one locality relaxation from input to output, right? Then two causal relaxations, 3 causal relaxations, 4 causal relaxations, up to the case where you relax everything, and of course the correlations here produced will certainly cover produce all local, non-local signaling correlations. Let's say the causal polytope fills in the entire simplex of probabilities. Yeah. Sorry? I think, why did we have colors here? Yeah, this is Danny is the artist in the team, so. But yeah. Mm-hmm. What do you mean? Here? No, we look at all the possible ways of having 2 input to output locality relaxations here. X3 connecting, so you have to think that there are many more, but many of them are permutational symmetries of these ones, right? So this is already filled with that redundant information filtered. No? And of course, let's say, as I was just mentioning here, of course, you can even, let's say, you can even attain signaling correlations, right? So we're not interested in that. We're just interested in the no signaling correlations produced. And it happens that, let's say, before the end of the hierarchy, you might already be able to reproduce all no signaling correlations, right? So this is what this definition involves. Let's say, so we say that a class is no signaling interesting if there exists no signaling correlations incompatible with it. Otherwise, we call it no signaling boring. So this one is certainly, let's say, no signaling boring because it produces all correlations, even signaling and no signaling. So therefore, certainly also the signaling ones. And what we show, for instance, in this case, we can show that these 5 classes are no signaling boring, right? So so in the end, this is like the complete causal hierarchy, but we will be interested in the no signaling interesting classes, right? And before I move to the next slide, so I have another definition here. So of course, for the no signaling interesting classes, so each no signaling interesting DAG defines a class of multipartite Bell non-locality, right? So whatever class that is no signaling interesting means that there are no signaling correlations outside of that. So whatever causal Bell class that is no signaling interesting means that there are no signaling correlations outside of it. And those no signaling correlations outside of it are non-local with respect to the causal model, and this defines classes of multipartite Bell non-locality in the inclusion sense, no? So, and yeah, so now what I do, so the difference between the next slide and this one is just that I will remove these 5 classes and I will focus now I will focus now on the remaining 10 classes, right? The no signaling interesting ones. Yeah. So this is the non-trivial, let's say the no signaling interesting part of the complete causal hierarchy for 3 parts, right? So our results, let's say, can be summarized by this theorem, right? So as I said, there are 10 no signaling interesting causal Bell classes, and 3 of which are equivalent. So there can be collapses in this hierarchy, right? So for instance, so these black arrows here encode the no signaling implications that come for free, that come directly from the construction, from the causal hierarchy. So namely, if a given correlation is compatible with this causal structure, then of course it has to be compatible with this causal structure, because all I'm doing from here to here is allowing for an extra arrow. And of course, if a no signaling correlation is compatible with this one, then it also has to be compatible with this one, because all I'm doing here is to add another extra arrow, right? So this is represented by the black dashed lines here. These are the no signaling equivalents that you get for free by having constructed such a causal structure. But then there are other no signaling implications that can happen, and this we have to prove. So in this case, we had to prove them by hand. It happens that these 3 here, they turn out, so let's say, I mean, in general, so the causality, again, the causal polytopes of each class is different, but when you restrict to no signaling correlations, they collapse into the same class. And a flavor of why that happens is by looking at this. So I mean, all 3 classes have the common property that if you trace Charlie's system, then what remains here is local. This is I mean, this can be seen in very few lines, and even intuitively. I mean, if I trace this out, what remains here is LHV. If I trace this out, it's easy to see what remains here is LHV. And if I trace that out, what remains for Alice and Bob is LHV. And from there, it's very easy to see that for the no signaling scenario, they collapse into the same class. So all of this here, you can see that. So coming back to the motivation to the paper in 2005, all of this here, so these 7, these 6 no signaling interesting classes happen to be within this classification of partially paired correlations, and therefore satisfies Svetlichny's Bell inequality, and therefore are violated by quantum systems. So in a sense, in the language of this 2005 paper, this was already known, if you want. But then there is this other class. So these 3, remember that these 3 collapse into the same single class. It is no signaling interesting. And what we prove here, what we prove in our paper, is that there are quantum correlations that are more non-local than totally paired correlations. So this class is not partially paired, it's totally paired, and we find quantum correlations beyond that. So as I was saying, when I was referring to the fact that those 3 classes collapse, the same intuition, I mean, so I was mentioning that if you look at the marginal of Alice and Bob, you get an LHV model for them. And from that fact, you can easily construct, so here I'm looking so from these 3 classes that were equivalent, I'm looking at the first one, right? The one involving just these 2 locality relaxations. And so it's easy to see because of the same reasoning that I was mentioning that, so for instance here, right? So if I trace this out, I still have something non-local between Bob and Alice. I can even have PR boxes here. If I trace this out, I still have something non-local from Alice to Charlie. I can even have no PR boxes here. But if I trace this out, I get something LHV. So what 5, okay. So, yeah, 5 is perfect. Yeah. So let's say so this gives us an intuition that I mean this from there we can show that this generic form of Bell inequalities have to be satisfied here. So what do I have here? I mean, what is this construction, right? So consider that you have a bipartite Bell inequality, right? And for instance, so A and B are measurement outcomes of Alice or our subsystem of Alice and Bob. And then we have, so Alice has also another subsystem, A prime, and B has also another subsystem, B prime, and C prime. And each E2 is a bipartite Bell inequality for the corresponding systems here. And this beta NS is the algebraic maximal violation of that bipartite Bell inequality. And beta L is the local bound of the bipartite Bell inequality. So, let's say it's easy to see that, so when you have two inputs and two outputs, this no signaling class is no signaling boring. So this class is no signaling boring because you don't have space for building this A and A prime or B and B prime for each part. But when you have two inputs and four outputs, it becomes no signaling interesting. And for higher alphabets, it satisfies Bell inequalities that are maximally violated in the no signaling sense by quantum correlations. And why they satisfy this inequality? Well, it's clear. No, I mean, as I was saying, so let's say if I look at it, so here somehow I can have even a PR box. I can have here a PR box. So from two of these three inequalities will always be maximally violated up to the algebraic maximum. Whereas for this marginal, I will always be restricted to LHV models. Sorry, this is my timer. Oh, sorry. Yeah, sorry. So from that construction, I mean, you see that, so for two inputs and two outputs, you take this inequality as being the CHSH, and then you see that there are no signaling correlations that violate it. Because you can have a PR box here, a PR box here, and a PR box here, and you violate that. And for higher alphabets, you can have inequalities that are violated by quantum correlations, right? So there is one example is the inequality that comes from the Perez-Mermin box that uses two. So the bipartite inequality that is violated by two singlets. This can be maximally violated with a finite number of measurements up to the algebraic maximum, or the chained inequalities that can be violated with a singlet only, but with you need many measurements on each part to have a high violation. So, I mean, here, let's say the conclusion is that you have quantum correlations that are stronger than totally paired correlations, and in a sense, this is the strongest form of multipartite quantum non-locality now. So it's even stronger than generally multipartite non-locality, and it's interesting. It's ironic that to build it in the lab, all you need to do is to use bipartite resources, right? So for instance, you can think that here is a photon, and A is the polarization, and this is the path of the photon. Then this is another photon, and here's the polarization and the path, and this is another photon, and now you need entanglement, for instance, between path and polarization, right? But, I mean, it's not so easy to do, but each ingredient, each bipartite ingredient of this inequality has been violated in the lab, right? Well, so the last part, we look at this other. So there remains another class which is also totally paired, and we call it the circle in the sense that so Alice communicates with Bob, Bob communicates with Charlie, Charlie communicates with Ali. So it's cyclic in that sense, and for that we don't know if there are quantum violations or not of the polytope, but we were able to characterize the full correlator facets, the facets of the full correlator polytope, and there you can find a new non-trivial Bell inequality tight in the space of full correlators, right? So it is interesting that this sort of non-trivial inequalities without a quantum advantage arises naturally somehow in this framework, right? But of course, there could still be the case that quantum correlations exist outside the Bell class, right? We didn't. The polytope is just too complex to characterize. I mean, so that's why we characterize the full correlator polytope, which is a projection of that. So yeah, so with that I'm done. So we studied how to reproduce no signaling correlations with causal relaxations, and we exploit the no signaling principles to simplify that and to lead us to a classification, right, given by this causal hierarchy. And there are, yeah, so one of the things that we show there is the existence of quantum tripartite super non-locality, as I like to play with that term, which was an open problem from 2005. And we also have this, I don't know, one a new full correlated Rayleigh inequality with no quantum violation. And perhaps an outlook. So, of course, as I said, in the case of this quantum multipartite super non-locality that we have, as I said, each ingredient has been demonstrated experimentally, but it would be interesting to see if it makes sense to make some experimental studies with that, and also to understand if the circle causal bell class is actually post-quantum or not. And of course, to see, well, super non-locality as a resource. No, for what? In the sense, one could look at these communication complexity problems, right? And yeah, so before I thank you, let me just, it's just an advertisement, so this has already been mentioned. There is a poster by Ranieri about serine distillation, and there's also a poster by Barbara about non-contextual wirings, right? So if people are interested in non-locality and contextuality as operational resource, there was also a paper that we posted with Rodrigo in the archive, which is in the same general framework, and some advertisement people might be interested. Right? So now, yes, thank you for your attention, and this is the reference.